In this separations video, I'll cover how to treat a non-optimally located feed. When you're doing this in practice, like in real life engineering, you would never want to intentionally send your feed to the non-optimal location. You always want to send your feed to the best place. But it can be useful to predict what would happen if, for example, next semester in your Unit Ops 2 course, you'll be using a distillation column, and you'll have the freedom to put the feed on whichever stage that you like. So it's useful to be able to predict what purities will occur. And I just said the key words. This is kind of like a predict type problem where you have N, you have the feed stage, or you're specifying a feed stage that may or may not be non-optimally located, and you want to predict what the purities are. So in this type of problem, again, you have the number of stages, you have the feed stage, and you have the reflux ratio. And your job as the engineer is to figure out what is going to happen. What will be the prediction for what purities you'll see? And from those purities, you can then calculate whatever molar flow rates you'll have as well. So for the purposes of illustration, I went to the McCabe-Thiele calculator, which I showed you about a couple of videos ago, and I put the following parameters in. I said alpha is equal to 3, z is equal to 0.4, xd is equal to 0.9, xb is equal to 0.05, reflux ratio is 3.5, and q is equal to 1. And this is the resulting graph I got. So it's telling me that I have 6 stages, and my best feed stage is on stage 3. Now, as I mentioned in a previous video, the McCabe-Thiele calculator is good only if you happen to have all the information that you need. So if you need to work backwards, the calculator won't work. So my question to you in this video is, what would happen if instead of feeding to stage 3, what if we feed to stage 5 instead? And to answer that question, we have to step the number of stages. So what we're doing here is we are moving stage 3 and 4 from the feed stage and stripping section into the rectifying section, and stage 5 is now our feed stage. So what we have to do is extend our operating lines. So instead of the McCabe-Thiele calculator, by the way, truncates these. So I need to extend my RSOL indefinitely like that. I also have to extend my SSOL like this. Right, so I'm just going to trace over them just to make it clear. This blue line is going all the way across, and this red line is also going all the way across. And I step my stages just like before, except instead of stepping over when it becomes advantageous to do so, I have to step the requisite number of stages. So if I move to stage 5, I would say 1 stage, 2 stages, 3 stages, and now on the 3rd stage, I have to stay on the red line because I'm still in the rectifying section. I'm still in the top section. Stage 4, I'm still in the top section. That line was crooked too, by the way. Stage 4. Finally, on stage 5 is the one that I step over. So now I'm going to step to the blue line. This is stage 5. And finally, stage 6 is down here. So this is like the reboiler stage. So I'll call this 6/ the reboiler stage is there. And as you'll notice, the XB that I get is not equal to XB from the problem statement. So XB is not equal to 0.05, which is a problem, right? I have to land exactly on XB in order to have a completely specified problem. So where did I go wrong here in this procedure? And that is because I had assumed that XD is still going to be at 0.9. What would actually happen in this case is my entire operating line would have to shift. So what I have to do now is guess and check a different XD. So in other words, maybe I would guess a different XD. Maybe I want to guess that XD is 0.8 or something like that. I'd have to draw a new operating line. So I'm going to draw a new operating line that starts at 0.8, but the reflux ratio is still the same. That hasn't changed. So I'm just going to draw a new operating line. And now my intersection point is still the same, right? So my new stripping section operating line is going to, this is subtle, I had to think about this for a moment, but if I guess a new XD, then my new XB must be set by material balances. Actually, no, ignore that. My new stripping section operating line has the same slope as before. I just have a different intersection point. Very subtly, it's just right below. So I would draw another stripping section operating line with the same slope. So I'd have to measure the slope from before. The slope after is the same, it just is intersecting at a different point. So therefore, my new XB would be somewhere around there. And I'd have to guess and check. So what I'm doing here is I'm guessing a new XD, drawing my new operating lines. I need to step the required number of stages, and I have to step the required number of stages in the section of the column that is specified. So I need to step 5 times off of the red line, and then on the 5th step is when I drop down, and the 6th step is the final one. Only when I step those required number of times and I land exactly on the XB that I had from drawing the operating lines is my problem specified. So that may or may not have been clear. Let me do another one just as another example. So I'm going to keep everything the same, but let's say we now move the feed to stage 2. All right, so same thing. What I'm going to do is, I know my purities are going to decrease either way, right? I know that if I have a non-optimally located feed, regardless of the fact of whether I move it up or move it down, my feed is going to not be located optimally. So my reflux ratio here, I specified this as 3.5. So that means my slope is 3.5 over 4.5, and it's going to be parallel to the rectifying section operating line that I had already. So I'm just going to make another guess. I like my first guess of 0.8. I think that's an informative point to draw. I'm just going to draw a line that is going to match the slope as best I can, drawing it by hand. It's supposed to be the same as this pink slope. Okay, so M here, M pink equals, let's just say MRSOL equals MRSOL. Right, signifying these are the same thing. Now I've got an intersection point there with the feed operating line, which does not change, by the way. The feed operating line is not a function of what stage the feed comes in at. So the feed operating line is still in the same place, and the intersection is still on both operating lines. It just has to do with where my stage stepping is occurring. So I'm going to extend this red line all the way. So my blue line, therefore, has to be, this is a point that is on the line, and I know that my slope has to be the same as before. So I'm going to draw a line like this and extend this blue line all the way as well. And this is my new XB that corresponds to the new XD. So based on my XD guess, I'm going to obtain a new XB. Okay, so now I can stage step. So I said I'm going to move the feed to stage 2. So my first stage is on my red line. So stage 1 is there. Stage 2 is then on the blue line, which interestingly, I'm stepping over. So this is maybe a bad example. Let's say I move the feed to stage 1. If I move the feed to stage 1, then my first stage is the one that I have to step over onto the other operating line. So this is stage 1, and then stage 2 goes onto the blue again. Oops. Stage 2 is there. Stage 3 is still on the blue. Stage 4, stage 5. Okay, so this tells me that I went too aggressive with my guess. I only got 5 stages. I should be getting 6 stages, and it should land exactly on XB. So maybe in this case, I would choose an XD that's a little bit greater, so maybe 0.85. This is the point. I would just keep going, guessing, and checking like this. And what I would recommend, instead of going crazy drawing lines on a graph, is again, set up Microsoft Excel and have Excel do your dirty work for you by setting up a solver equation that you can use. All right, so that is going to be it for this video. We still got one more video. I'll try to make it short for today.